Hello, let's make a simple tile-based platform game.
And as is customary, I like to start these videos by showing you what we will be creating today. And you'll notice that it's quite graphical today, but that's the least important part of what we'll be working on. Let me introduce to you Jario, or Super Jario. He's definitely not an Italian plumber. And even though Jario obviously does not know how to run properly and floats all over the place, he has many similarities to his Italian counterpart. And so the engine we're going to be working on today is a tile-based engine. You can see we can collect coins and things, and it's really about how do we handle the collisions between the tiles in a sensible way. And what I'd like to get out of the way right up front is this is not complicated at all. In fact, we're not going to be looking at any physics or geometry intersections or anything like that. It really does exploit a few little quirks of floating point numbers and 2D arrays. We'll also be looking at how the camera pans around the level. So we can see here as we get towards the level boundaries, Jario becomes off-center from the screen, but the camera will follow Jario around as he moves around the level, just like we did in the Worms game. We'll also spend just a little bit of time talking about the dynamics of the character, getting the feel of the character correct. So when he jumps, he jumps in a controllable and responsive way, but he doesn't sort of break all of the rules of physics, and this will encourage the player to develop a skill set in order to control Jario properly. Now you may have noticed the ominous number 1 at the end of this video title, and that does imply, of course, that this is part of a greater series. And it will be, but not in the same way that the Code-It-Yourself Worms games was a series. The reason being is I think platform games are an excellent vehicle for delivering all sorts of additional material about how to do other parts of the game. But this first one will be quite complete. We will just talk about how we create tile-based levels using a tile mapping strategy, how we control the camera, how we control the player, and how we handle the collisions between all of the above. Let's get started.
Now you may have noticed that all looks quite graphical, and we'll make it look graphical towards the end of this video, but to start with we're just going to be drawing coloured rectangles on the screen, and this is a simplification that I think is necessary to really understand what the engine is doing beneath.
As usual, I'll be demonstrating everything using the OneLoneCoder console game engine, which you can download from the GitHub. The game engine is a simple class which handles drawing to the screen and user input, and all we need to do is fill in these two methods, onUserCreate, which we can use to allocate resources, and onUserUpdate, where we do all of the fun stuff. I'm creating an instance of my new class called Game, and I'm creating a console which is 160 characters wide by 120 characters high, and each character is 8 by 8 pixels.
For now.
When we talk about tile-based games, we typically talk about a two-dimensional array of something that represents a space. The 2D array is broken up into rows and columns. As you can see here, I'm drawing them out, 0, 1, 2, 3, 4, 5. And we fill a particular cell within the 2D array with information that defines what we want at that cell. So for example, let's say I want a solid block here. I'm going to use the hash symbol. So here's a little platform of 3 solid blocks. For empty space, I don't like to use space, I like to use the period character, full stop. And that way I can count how many spaces I've gone across the screen. And the nice thing here is that we know that all of the tiles lie on integer-aligned boundaries. So for example, this point here would be 3, 2, 4, 2, etc, etc. And this implies that our tiles are 1 by 1 in size. And this is it's unitless space, but let's assume it's 1 unit that way, and it's 1 unit that way. Working in a unitary space like this has lots of advantages. Firstly, I don't need to store any of this geometry. Everything is implied by its position in the array. We can extract the location of where that tile is, and we know its width and height. Now, let's say I take an arbitrary point somewhere within the tile map. For example, I'm going to assume this one is about 2.43169 by 3.247. Clearly this point is using some non-integer based numbering format. In fact, we'll probably be using the 32-bit float. Well, it's easy to work out which cell this point is in, because all we need to do is scritch out the fractional part. And this is really nice, because we don't need a complex system of searches to work out where we are inside our tile map.
I think this approach is quite elegant, and we'll be exploiting it for all aspects of our platform game.
For example, if I wanted to track a particle and then see if it collides at any point on the map, let's say it's moved to here from one frame to the next, accessing that information is really trivial. We just simply X and Y into our 2D array to extract whatever character is there. So in this case, if it's equal to the hash symbol, a collision has occurred.
There are some caveats to this approach. It does assume that each tile is a rectangle or a square and its boundaries are solid. So if we wanted pixel perfect precision in our collision detection, we'd have to go one step deeper. We're not going to do that in today's video.
So let's start by defining the level, and I'm going to represent my level as a string. And I'm also going to store the width and the height of the level. As integers. I'll create the level in the onUserCreate function. And I'm going to declare the level for now to be 64 tiles wide by 16 tiles high. Don't forget, a tile currently is unitless. And the nice thing about using a string to represent your level is it can be quite graphical. So we've got 16 rows of level. And I've not created a 2D array, I'm just simply appending it all to one big string. Now designing the level can be quite fun. Using the insert key, I can put in hashes wherever I need them. Take that, Visual Studio Code. And so I'm going to put in a ground plane. So this is just a single plane going across the level that the character can't go below. But in order to test collisions, we need to have some features in there. So let's put in a small staircase of some description. And you can see I'm being quite haphazard with this. I'm not going into too much detail. But we don't want to design levels straight away. What we need is more of a playground that we can use to test the collision. So I'm going to put in a single block on its own, and I'm also going to put in a more complicated form here for the character to try and navigate. And I always think it's useful to have some sort of tunnel as well, because this will really test the power of your collision detection routine. And you'll notice that my tunnel is one cell wide, and this is quite important because in some collision detection routines you may find that things get stuck when the cells are just simply one space apart. It's also quite important that we give an exit so that the player can get back out into the real world. So we'll just put that in too. Deciding which part of the world we're going to be looking at requires a camera. So let's add in a camera position X and Y variable. And as the game progresses, the camera position is going to change, at which point we want to draw the level.
And it's during this draw level phase that we give the world some scale. We start to attribute size to things.
So to convert from my unitary tile map space into world space, I'm going to assume that each of my tiles are 16 by 16 pixels. And this means that by using the screen width and screen height functions, I can work out how many tiles are visible on my screen. On a computer display, the top left is always 0, 0. And we probably want the camera to represent the middle of the screen. So I'm going to create two more variables which represents the offset from the middle of the screen to the top left, and this is simply taking our camera position and subtracting half the screen's dimensions in both axes. I don't want the camera to disappear outside of the level. I want it to stop when the camera position is close to the boundaries of the level. So I'm going to clamp it. And in this case, if the new top left position goes less than 0, I fix it to 0. And I do the same for the other side. But in this case, instead of checking for the level width, we're checking that the offset doesn't go beyond the level width minus the visible tiles on the screen for that axis. Because we want to display at least one whole screen on the screen. Now we know where our camera is, we want to draw tiles to the screen. So I'm going to create two nested for loops for X and Y. And these are the same size as the number of visible tiles on the screen. I feel at this point we're going to need a couple of little utility lambda functions. I'm going to create one called getTile, which takes the X and Y coordinate and returns the character in our string for that location. But I'm going to do some boundary checking as well, because I don't want to get any invalid memory accesses. So we'll make sure it's in bounds in the X direction. And we'll also check the y-axis. If it is within bounds, I'm going to return the character at that point in the string, simply by accessing the string as a single dimensional character array using our good old favourite y times width plus x. If we're not within bounds, I'm going to get it to return a space, which represents our null character. It's not quite the same as a full stop space, but perhaps we can use the space character to indicate an error has occurred. Usually whenever there's a get, you also have an accompanying set. So I'm going to create the same thing, but to set a particular character within the 2D location in the string. Going back to our drawing routine, I can now extract a character from our string for a given location. I'll call it tile ID. And we'll use the lambda function we've just created, and we'll pass into it the x and the y coordinate. And all we're going to do with this ID is work out how to draw it. So if it's a full stop, we probably want to draw some sky. Come back to that in a minute. If it's a hash symbol, we want to draw something that's solid. And if it's anything else, we're just going to draw black. So if it is a period which represents nothing in our game, then I'm going to use the OneLoanCoder fill command to draw a rectangle in that location. So I'm taking the x and y values, scaling it by the tile width, and I'm also taking the x and y values plus 1 each and scaling those two, because we're going to be drawing a square from the top left to the bottom right of that rectangle, and I've chosen the colour to be cyan. Let's take exactly the same code for hash, but I'll set the colour to be red, to indicate a solid surface.
You're probably already thinking ahead that we can overwrite these later on with sprite drawing routines, and we will.
Let's now add in the ability to control the camera's position. I'm going to add in something for the camera to follow, which will be a player. So I'm going to create two variables, floating point, which represent the position of a player. And we know for later on, we're also going to need some velocity component as well to move the player's position. And just before we draw, I'm going to set the camera position to the player position. And you might think, well, why are we doing this? Why do we not just use the player position directly? Well, the truth is, I don't know what we might want to do with the camera compared to what we want to do with the player. Perhaps for a cutscene or something, I want the camera to go somewhere else. Perhaps I want it to judder and shake around. But I don't want to change the player's position in order to emulate this effect. But for now, we'll just assume there's a one-to-one relationship between the two. Handling input in the console game engine has always been quite simple, but I've made some modifications to make it even simpler. And the first thing I've added is an isFocused flag, and this will check whether the command window actually is under focus. Some of you may have been experimenting in the past and noticed that when you're typing things in a document, stuff is happening in your console game engine application. You can still do that, but now you can filter out whether the window is highlighted or not by using this routine. I'm going to add controls for the up, down, left and right directions. We'll add player physics in a bit, but for now I just want to test the collisions. Now, instead of using the M keys directly, I've nice and tidily wrapped that up in a getKey function. So you just pass now which key you're interested in, and it works exactly the same as before. It's just a little more consistent. So if the player is pressing the up key, I want to change my player's Y velocity. And in this case, I'm just going to set it to -6. Now, you might think, where have I got 6 from? Well, these are values I've tried and tested. I don't want to show the experiments to get there in this video. In a similar fashion, let's add in down. And I'll also cut and paste in for left and right, but we'll make some changes. Obviously, we're working in the X direction. And for moving left, we are going in the negative direction. We'll just change this to left too. And for right, we're going in a positive direction. What I will do for now is, before any of this happens, I'll set these velocity values to 0. X and Y. And we'll use those velocity values to update the player's position. So the X direction becomes the X direction plus the velocity times F elapsed time. which is the time between the last frame that was displayed on the screen. And it's important to use f-elapse time to smooth things out, because we don't know how long it takes to update a single frame, but we want the user experience to appear consistent. After we've drawn the map, we also then need to draw the player. And I'm using the fill routine again to draw a green rectangle that represents the player's position. The main difference here, though, is you'll see that I'm subtracting our offset position, which we calculated up here, from the player's current position. And this will neatly wrap up what happens when the player has approached the boundaries of the level. So I've done that for both the X and the Y axis. In contrast, when I'm getting the tile from the array, I want to add the offset. So in this case, the offset is moving us further into the 2D array, and in this case, the offset is pulling the player back into the screen, the viewable area. So let's take a look and see where we're up to. So we can see we've got the cyan background, which represents empty space, and I've got a green rectangle moving smoothly around, representing the player with the arrow keys. I can see a red rectangle, and I can move around the level. In fact, there's the level we can see we decided in the string, so there should be a tunnel down here somewhere. There it is. And we'll see things aren't quite lining up yet. Fair enough, fine, we're not quite there. But everything seems to stay wrapped around tile boundaries. As in, you can see we've got this jerky movement. We need to smooth out the map moving around. And one final test is as the player approaches the edge of the level, we can see he moves over to the side of the screen.
Not that impressive so far, but let's see if we can make it a bit tidier.
The first thing I want to change is the number of tiles that I've got on the screen, but instead of changing the screen resolution, for now I'm just going to change the size of the tiles. And everything that we made was adaptive and can accommodate that. Very nice. The second problem we saw is that the background tiles only seem to move in integer values, and this is completely understandable. Because our X and Y location moves in integers, we grab an integer tile from the array and we're drawing out to integer clamped boundaries. We had a similar problem with the Code It Yourself Frogger game. But in this case, what I'm going to do is calculate some offsets into the individual tiles to work out how much to displace them by when we draw them on the screen. So let's see what this means. We know that our map offset value, in this case f offset x, is continuous and can have decimal points quite legitimately. After all, it just really tracks where the camera is. This code here gives me the fractional part of the floating point number. And because we know that we operate in unitary space, this is very easy then to map onto how much of a tile does that fractional component represent, because we simply multiply it by the tile width. So if we're up to 3.5 as an offset here, this becomes 0.5, and we know that we're half a tile into the offset. I do this for both the X and the Y axes. Now that we know our tile offset, we don't want to draw clamped to integer tile boundaries, we want to apply the offset instead to when we draw the rectangles. So in this case I'm subtracting the offset from the X axis. I'll do it again for the Y axis. And with this fill routine, you don't specify width and height, you specify two absolute coordinates, so we need to also add it to the next two parameters. I'll just make sure that's a Y. And instead of typing all that out again, I'm just going to replace our solid block with the same code and change the colour to red. So now we're drawing our rectangles. Instead of being on integer aligned boundaries, they are integer aligned boundaries, but also offset a little bit depending on where the camera position is. So let's take a look. As I move my green rectangle across the screen, we can now see we have reasonably smooth movement. In fact, it's much smoother than it was. And it seems to work in both the X and Y axis. The camera clamping is working nicely, but we can see towards the edges of the screen, we've got information popping in and out. So it doesn't look quite right. The boundary at the bottom seems a bit distorted, and the boundary on the right-hand side doesn't seem very well either. Well, one way to approach this, and it's a little bit lazy, is to simply overdraw everything that we need. So instead of just drawing from the precise number of visible tiles, I'm going to draw to a +1 boundary of tiles around the visible screen. So this has now got rid of all of the edge artifacts that we've just seen.
Right, now we have reasonable movements and camera control, let's handle what this video is really about, and that's the tile versus tile collisions.
Let's start by making some assumptions. So here I have the player character Tile, and in this case he's 1 unit wide by 1 unit high, as evidenced by the coordinates in the 4 corners. And we're going to make some assumptions. For example, everything in the map is also a tile, so this tile will only be colliding with other tiles. For example, we won't have it colliding with some awkward shape. And if this assumption is true, that means we only need to check the 4 boundary points of the player tile against the scenery tiles to see if there are any collisions. We know that we also have a velocity vector associated with the player tile. We'll call this one Vx and Vy, for example. So we can predict where the player will be on the next frame, and in a typical collision detection routine this is exactly what you would do. You would work out where the player potentially might be, check if there are any collisions, and resolve them. However, treating the vector as a vector leads to some quite challenging problems, to which there are no solutions. Let me explain. Let's assume that this top tile is my free-moving player tile, and that this tile is a static tile as part of the scenery. We've just updated the velocity vector and then just updated the position vector, and it works out that we're going to be colliding with the diagonal corner of the scenery tile as described by this image. What is the correct course of action here? Do we displace the player tile that way? Do we displace the player tile that way? Do we displace the player tile in both directions? Some situations this may be more obvious than others. Perhaps displacing by the minimum direction of overlap is a good strategy. So we know how much y has overlapped here and how much x has overlapped, and perhaps if dx in this case is less than dy, that's the minimum amount of movement. So we choose to displace the player sprite in the x-axis. And this is also starting to bring in geometry and some, well, simple but still the mathematics, which I don't think we need to do. In fact, I'm going to just exploit the fact that we can round floating point numbers to sort out our collision. So let's go through this. I'm going to create 2 new variables, which are new player pos x and new player pos y. Now you see why I didn't add plus equals here before. And so, if unhindered, this is the location the player will end up in. So at this point we want to check for collision. We've got some new positions. I'm going to start with the x-axis. And I only need to check for collisions in the direction that I'm going in. So if I'm moving to the left, i.e. the velocity is less than 0, I want to do something, or else I want to do something else, the player's moving right. And because my player is a rectangle and I'm only doing sort of rectangle-rectangle collisions, I want to check 2 points on my rectangle, the top left and the bottom left in this case. So top left is given by the 0, 0 coordinate relative to our player position. But I also want to check for collision with the bottom left. And you may notice there's a whole lot of interesting things going on in this line. But this is one of those things that it's easier for me to type it out first and then explain it. In the event of either of those 2 points colliding, what I'm going to do is set the x position to be the requested position cast to an integer plus 1. i.e. we get rid of the fractional part and we add 1 to it. I'm also going to stop the velocity. So there are 3 things here which need a little bit of explanation. Firstly, why are we using new player pos x and old player pos y? Secondly, why are we using the x-coordinate 0 and the y-coordinate 0.9? And thirdly, why are we casting to an integer? Well, before we draw some more tiles, I'm just going to add in the code for when we're moving towards the right, which is very similar code except our coordinate location is slightly different. In this case, it's the opposite side, so we've added 1 to the new player position x. And in the event of colliding on the right-hand side, we still cast to an integer, but we don't add 1 to it. Okay, well the first point there was why are we using the new position x and the old position y? And that is simply to remove the y component of my velocity vector. So I really am only checking in one direction. And this means, as described before, I technically can't ever have a diagonal intercept problem, where I've got to choose between an x and a y axis. All I'll ever have to solve are x collision problems. So I'm retaining everything just being in one axis, which is much simpler to solve. And if you do actually end up implementing things like conservation of momentum and stuff like that, which we're not for this video, this also makes things simpler too. So point 2 was when we're testing in the x direction, why are we adding 0.9 to the y instead of 1? So let me just fill these in. So instead of at 1 there, we're adding 0.9. And the same applies to that side. Why are we doing this? Surely this is untidy. Well, let's consider a situation where I've got my sprite tile of the player resting upon a scenery tile. If the player is moving towards the left, I'm checking this point and this point. And don't forget, all of our tile data is stored in a 2D array. So let's assume our px and py values are equal to 3.2, 5. As I'm moving the character towards the left, I want to be checking these 2 points against my array, which would resolve to something like this. So 3.2, 5. And without the 0.9, we'll also be looking at 3.2, 5 plus 1. Well, of course, this 3 at 0.2 gets rounded down to 3 because of truncation. That's fine, that's great. And this 3 represents which cell in the x-axis are we in currently. However, for the y component of this map check, we notice that this actually truncates to 6, which means our checkpoints are actually in 2 different cells in the y-axis. But this is completely irrelevant because we're only checking in the x-axis. And in this situation, let's assume that this cell is indeed solid. When this collision detection returns, it'll return, well, yes, I'm in a solid cell. And we've just checked that if either this point or this point are within a solid cell, then a collision has occurred. But clearly, in this scenario, it hasn't. The player is walking across the surface. So by adding 0.9 instead of 0.1, I mean, to be fair, this really probably should be 0.99999, but it's okay, it works out. 0.9 is fine. When this gets truncated, instead of becoming 6, it remains as 5. So we're making 2 points of check in the same cell. So then your next question may be, well, why are we doing 2 checks? Well, let's consider this situation where we've got a solid tile and the player is actually between 2 tiles. So he's not walking on the surface, perhaps they've just jumped. And we're checking for the x direction along here. So at this point, the y's are separated. And this is an equally valid stop. So in this situation, it may very well be that we're checking for 2 different y locations, but it's completely fair and valid. So in effect, what we're doing is just shrinking the cell slightly so it doesn't get a false positive hit for the collision. And we'll be changing which side of the cell we shrink depending on which collision direction we're checking for. So the third point was, what's the deal with casting things to integers? Well, let's take this scenario where my player sprite has collided with a solid tile in the x direction. We know that tiles lie on integer aligned boundaries. So let's assume that one's 4, that one's 5, and somewhere we've got 6 in our x direction. When we're checking for a collision along the left hand side, we'll know that in this case px may equal 4.8, for example. It's overlapped slightly into this 4 block. We've already determined that a collision has happened. So how do we correct? Well, instead of calculating the point 2 and displacing the player back along the x-axis, it's very simple to truncate the floating point number, i.e. get rid of its fractional part, add 1 to it, and that gives us a precise boundary at where our player should sit. That's moving left. If we reverse the situation, so I'll just make this one the solid block, and we know again that our player's position is about 4.2 this time because it's overlapping into the 5th block along. In order to align it to that boundary, we simply truncate. We don't need to add 1 to it at all because we're moving right now. We want it to clamp back towards the 4th boundary.
And it goes without saying that all of these things that we're doing in the x-axis apply to the y-axis.
So just to recap, we're using the new x position and the old y position to get rid of the y component of the velocity vector. We're checking with a plus 0.9 offset instead of a plus 1 offset to make sure that truncation doesn't catch us out, and this will allow the character to fit in gaps that are only 1 unit across. And finally, we're using truncation again to align the player to a boundary in the event of a collision occurring. I'm going to use very similar code now for the y-axis, except this time we don't want to separate the x and y velocity component vector. We have now resolved collision in x, so we're going to use the new x position and the new y position. So that's handling velocity going up the screen, i.e. the velocity is negative. Let's also handle velocity going down the screen. Once we've handled the collision and we know that our collision detection routine has displaced the objects, we want to update the player's position with the new player position. So let's take a look. Well, we can see now the green character cannot go below the red line, and we'll try against our single block. We'll try and get some diagonal collisions as well. You see, it's quite robust against the single block. So let's try it against the staircase. That's fine too. Try it on all sides. It's good to make sure that we come up with a proper testing ground for these things. I want to fall into the gap. There we go. It did take a little bit of alignment to get right, but it's in there. And we can follow the tunnel all the way around. I'm trying to press different keys to make sure that the block doesn't get out of control. And we can see we can get back out again. Just line it up. Very nice. So this is a really robust and pleasantly simple collision detection routine for a tile-based game.
And I like it because we've done no geometry so far. Now let's add the fun stuff.
Well, the first thing our game is going to need is some gravity. So I'm going to force some gravity by forcing the y velocity to increase by a certain amount each frame. And since we're going to be playing with velocities, I'm also going to clamp velocities to stop them becoming out of control. So in this case I want a maximum velocity of 10 in the x direction, minus 10 the other way around, and for y I want 100 and minus 100. Now because I want the character to accelerate in a particular direction, instead of just fixing the velocity to a set amount, I'm going to modify it. In this case, by f elapsed time, modulated by a constant. And if you're familiar with some of the videos, you'll notice straight away that this is indeed now acceleration. I'm going to remove setting the velocity x and y components explicitly because now they're going to continue between frames. Let's add in the ability for the character to jump. And he's going to jump on the space key, and it's when the key is pressed, not released or held, so it's a single event. And I'm going to make a rather crude check that the player has no current y velocity, i.e. they're not already jumping or they're not falling. There is a small instance, maybe at the very top of a jump, you might be able to jump again. But there's a way around that, and we'll see that later. So in the case of a player jumping, I am just going to physically force the y velocity to be a set value. I'm going to leave in the up and down keys because it's useful for testing things, but functionally they won't have anything to do with the game. It will just be the left key, the right key, and the space key to jump. So let's take a look. So the character has fallen with gravity and he's been stopped by the collision detection routine. I can make him jump with the space key. He accelerates very slowly, and it does feel as if everything is in ice physics. It's all a bit slippy. That said, I can get him to fall down this gap. Probably can't. Oh, there we go. Yeah, so we can, as long as he's going slow enough not to clip the other side. To stop it feeling as if we're always floating around on ice, I'm going to have a flag which detects when the player is on the ground. And we know when the player is on the ground because there will have been a collision in the y-axis vertically. So if that collision is true, then I'm going to set this flag, player on ground, to true. It's important though that we remember to clear this flag before we do the test. And just beneath where we've put the code for emulating gravity, I'm also going to put in some drag. So if the player is on the ground, I'm going to use a proportion of the current x velocity to work in the opposite direction of the current x velocity. And I'm also going to check that if the velocity is near zero, to actually clamp it to zero. We want the player to be able to stop. So now I have the player, and we're accelerating in the x direction, and I let go, and you see he comes to a gradual stop. It's a little bit more pleasing. However, when the player is in the air, the drag doesn't apply. Speaking of which, I want the player to have some control whilst he is in the air, but I don't want them to have the same amount of control as when they're on the ground. So I'm going to change this velocity vector component depending on the player on ground flag. And this allows me to have that Mario kind of feel, that you've got lots of control whilst the player is on the ground, and you've got a little bit of corrective control, i.e. you can slow the player down when he's in the air. You can't make the player go back on himself though.
I'm going to spend some time now turning the rectangles into imagery, as in we'll use some sprites. but I'm also going to need to scale some of the velocities and the resolutions in order to make everything work well. The original Nintendo Entertainment System used a 256 by 240 pixels as its output. I'm going to do the same.
And so I'll start by specifying the resolution for the console to be the same as the original Nintendo. I don't think it's that necessary to talk through changing all of the rectangles into sprites, because we've done that before in quite a few other videos. So I'm just going to whiz through this quite quickly. Right, just trust me, there was nothing that interesting about any of the code that I've just written, but now we can see we've got the character, and we've got the ability to jump. We can see I've not quite set yet, when he hits the ground he doesn't stop jumping. But I've got a nice feel that the character is under control. It's taken me a while to find the values, but it kinda works. Very nice. Let's just see if we can make him put his legs down. And the reason being, when the player hits the ground, I need to tell it which row of the sprite sheet to use again. And I'm using a variable ndirmod x and ndirmod y represent which sprite of Mario to actually display. Sorry, not Mario, Jario.
Have to get that right. It's Jario, not Mario.
Let's try that again. So he jumps and lands. Very nice. We'll add running, perhaps at a later series of the video. I'm less bothered about sprite animation stuff. I've made a handful of changes. In this case, we can specify with a capital G a ground tile. And with the capital B, we can have some bricks, and a question mark is clearly a question mark block. They don't do anything at the moment, but they look different. But you can't have a Mario game without some coins. So I'm going to use a lowercase o to represent coins. Firstly, let's just see if they draw properly. Very nice. But right now the coins behave like a solid object. We want to check for pickup collection before we handle the collision, because we don't want the pickup to cause a collision if the player can actually pick it up. So we take the new position x and y, and we're going to check the 4 corner boundaries, and in this case it will be +0 and +1. Not 0.9 as it was before. And I'm doing this really quite simply and naively. I'm just simply checking, is that point a coin? If it is, then set it to background space. For now, I'm not doing anything else. I'm not increasing a counter or anything else. This is just to show you that yes, you can interact with the tiles that you hit. And we need to do that check for all 4 corners. Now, as the game increases its number of pickups, there'll probably be a much more elegant way to do this, and we'll explore that in a later video. But for now, I'm just setting the background tile to be equal to sky. Let's try that out. He jumps up, and he can collect the coins. And so that's almost that. I will add one more little thing though, and that is for the purists here. Currently the console game engine uses the Consolus fonts, and I've chosen that because everybody has that font. However, it's not always the best, and you may have noticed that in some of my videos there's a sort of a pixelated look. Now I quite like that look, and that's why I keep it, but there are some fonts on your system you can choose. You may not have this one, but there will be something similar. It might be worth trying a few different ones, which render it just like real pixels. And this is where we start to see that the console really can be used as a complete game engine in its own right. It might be a little limited on colours, but it certainly isn't limited on resolution and display and performance. You'd be hard pressed to tell that this is in fact running in a command line.
And so there you have it, a very simple tile-based platform game engine. I like the fact that it uses very simple tricks of computer numerics instead of relying on geometry to do the collisions. And I think this will be an interesting platform, excuse the pun, to move further on with looking at how we can do things in platform games. So we've got enemy characters to add, moving platforms, different types of pickups, game structure, where I can see this one developing into quite a few interesting videos. Anyway, all of the source code is on GitHub as usual. Please download it, hack it, have fun with it. If you've liked this video, give me a big thumbs up, it really does help with my self-esteem, and have a think about subscribing. I'll see you next time. Take care.